Hi. In this set of notes, we're going to go over the Summing Forces Physics Journal. So, our guiding question for this is how can you stay organized when solving for unknown forces? The big idea here is that forces can be summed by looking at the horizontal direction and the vertical direction, right? Horizontal, we're going to call the x direction, vertical direction is the y direction. Um, into components. So, right, see our notes on vector components if you don't know what I mean by the x and y components. So the directions. So the first, and the nice part about this is it's just following these directions on all the rest of the problems for this unit. So the first step is to draw a force diagram. So we've been doing lots of practice with those. So hopefully we're getting pretty good at that. The next step is to pick a coordinate system. Generally, it's the standard y is straight up and down, x is side to side coordinate system. Though when we get into inclined planes, we're going to have to do a little bit of changing with that. But that's typically your coordinate system is your standard like y is straight up and down, x is side to side. We'll do that during the example problem. Put any diagonal forces, meaning that forces are not aligned with your coordinate system, into the x and y components. Next, add all the forces in the x direction, set it equal to the net force, and solve for any unknowns. And then, right, 5 would be the same thing. Add all the forces in the y direction, set it equal to the net force, and solve for any unknowns. So we're going to go through and demonstrate how to do each one of these steps. Here's our first example. A 50 Newton force is applied at a 30-degree angle to a 200 kilogram block. Find the normal force and the force of friction. Okay, so here's just a little picture of it. We got a block, we got a line coming off the side there. So let's go ahead and follow the directions. First one is to draw a force diagram. So let's see here. Here we go. First step, draw a force diagram. I went ahead and already drew it here for you. So there we go, done. Okay, next it says, let's pick a coordinate system. Okay, so when we go to do that, what we'll do is we'll call, right, up be the y direction and right, that be the horizontal direction, be the x direction. So that's our coordinate system. Okay, number 3 says split any diagonal forces, which are forces that are not aligned with your coordinate system, into the x and y components. So any forces that are not either straight up and down or horizontal need to be broken into a horizontal piece and a vertical piece. So that's going to be talking about this 50 Newton force right here. So that's at a 30-degree angle here. So let's go ahead and do that. So when we go to break it into pieces, and if you need to look back on how to do this, you can look at the vector component notes again, but you just break it into a horizontal piece. Typically we use a dotted line and a vertical piece, right? And that turns it into a triangle, right? So this piece right here, the horizontal piece, that's going to be 50, the hypotenuse, times by cosine of 30. Cosine because it is adjacent to the 30-degree angle. And this part will be 50 sine 30 because it is opposite from the 50-degree angle there, or sorry, from the 30-degree angle. So that's steps 1 and 2 and 3 done, right? So now we have things are all either horizontal or vertical. So now we can move on to step 4. Um, right, step 4, which says add all the forces in the x direction, set it equal to the net force, and solve for any unknowns. So here's how that's going to look. Um, so we start by putting this notation here. So the notation looks like this. Sum of all the forces in the x direction. This is just notation that sits in front and looks nice. So that's just notation. That says what you were doing. Okay, so this little symbol right here just means to add up. F means for forces in the x direction. So I'm going to add up all the forces in the x direction. The next part is the net force. So we know that horizontally, the net force is equal to 0 because it's going at a constant speed. I guess it doesn't say that, but let's assume that it's going at a constant speed. That's just me writing a poor problem. I apologize. Let's assume it's going at a constant speed. So 0. Okay, so this is the net force. That's what goes here. Okay, so then equals, so over here, you're going to sum the forces in the x direction. So that's going to be forces that are to the right minus forces that are to the left. So that's going to be 50 cosine 30, because that's our force to the right, minus the force of friction, because that's our force to the left. Okay, so okay, and when I say sum, what I really mean is, right, the forces to the right minus the forces to the left. So it doesn't necessarily mean like sum, sure, I guess it's plus negative force of friction, but I don't generally write it that way. Okay, now as we move on, we can kind of ignore that the notation sits there. You still need to put it there. I want to see that, but that's just to keep yourself organized. So the next step for us is going to be to add the force of friction to the other side. So that's going to give us force of friction is equal to 50 cosine 30. And then we can just type that in, right, into our calculators. 50 times by the cosine of 30 is 43.3 newtons. So next, right, we do step 5. So step 5 says add all your forces in the y direction, set it equal to the net force, and solve for any unknowns. So we'll go ahead and do that. So sum of the forces in the y direction. Vertically, because right, this object is not accelerating vertically, right? It's not flying off the floor or off the ground. It's also not sinking down into the ground. So the sum of those forces are also equal to 0. And then we do our up forces minus our down forces. So our up forces will be the normal force plus the 50 sine 30, okay, minus the force of gravity, right? Positive because they're up, negative because it's down. So that's our writing the equation. So in this unit, right in the last unit, you were using, like the Paul, John, and Ringo equations. And so you'd like have to decide which equation to use. In this one, you're basically writing your own equation each time. So there's no like trying to figure out what equation or trying to memorize these equations. You write it straight from like looking at this diagram right here. That's why the diagrams are so important, being able to do them. So the next thing to do is we're going to solve for the normal force. Right, it says find the normal way up here. It says find the normal force and find the friction. We already found the friction, now to find the normal force. So we're going to go ahead and we will move the force of gravity over to this side. So that's going to give us force of gravity is equal to normal force plus 50 sine 30. We're going to subtract the 50 sine 30 over there. And so that's going to give us, I'm going to go ahead and switch the force of gravity to be m times g. So that's going to give us the force of gravity, m times g, minus 50 sine 30 is equal to the normal force. So that's going to be 200 times 9.8 minus 50 sine 30 is equal to normal force. So therefore, the normal force is equal to, so 200 times 9.8 gives you 1,960 minus 50 times sine 30. So that's going to give you 1,935 newtons. There you go. There's solving that one. Okay, let's keep going. Let's go ahead and do example 2 as well. So a 0.5 kilogram mass is held by two strings, each make a 40-degree angle with the horizontal. Find the tensions in the strings. So here's my little picture, I guess. This is a 0.5 kilogram mass. We got our two strings there. So let's go ahead and follow our directions. Step 1, draw a force diagram. Okay, so let's go ahead and draw a force diagram for the mass. So we're going to have right, gravity down, of course. So we are also going to have tension in the direction of the strings. So, right, we'll call that T for tension. And we also have, and we'll call that T for tension, right? We've got two tensions there. Now, since the angles are the same, right, 40 degrees for both, the tensions will be the same. So I can call them both T. However, if one angle was different than the other, then I'd have to call them T1 and T2. That makes it much more difficult. And we're going to do an example problem, but we'll wait till we're much later in the unit. So, but because the angles are the same, I can call them both T. So they're the same thing. Okay, going back, next up, we're going to pick our coordinate system. We're going to use the same coordinate system that we were using before. So that means that, right, that will be up and down will be our y direction, and side to side will be our x direction. Okay, next, number 3, split any diagonal forces, meaning forces that are not aligned with your coordinate system, into the x and y components. So for us, we have two of these, right? We have two diagonal forces. We have tension and we have tension. Those do not align with our straight up and down or side to side forces, so they need to be broken into pieces. So right, each one of those gets broken into the horizontal piece, and they also get broken into the vertical piece. Over here. And then we can label them with sines and cosines. So this is going to be the hypotenuse times by sine of 40 degrees. This one is going to be same thing, t sine 40 degrees. This bottom one here is going to be, right, it's next to the 40, so that's going to be t cosine 40. This is also t cosine 40. Okay, so now let's take a look at our next step. Add all the forces in the x direction, set it equal to the net force, and solve for any unknowns. So let's do that. Next up is to sum of forces in the x direction. When we do that, we know that like in the horizontal direction, we are going to have a net force of 0. The reason we know that is because this object is not accelerating side to side. In fact, it's not even moving side to side. So we know it's got to have balance forces. So then forces to the right, t cosine 40, minus forces to the left, t cosine 40. And we're actually kind of stuck here because in this case, this doesn't tell us any information. Of course, t cosine 40 minus t cosine 40 is equal to 0. So that's not helpful. So we're kind of stuck. Since anytime we get stuck, we just move on to the y direction now. So the y direction, sum my forces in the y direction. We also know that the net force in the y direction is equal to 0 because this object is not accelerating upwards or accelerating downwards. So remember, for this, you do ups minus downs. So that's going to be, the up forces are these t cosine 40s. We have two of them. So t sine 40 plus t sine 40 minus the force of gravity. Force of gravity is negative because it's downwards. I can simplify this a lot, right? T sine 40 plus t sine 40 is going to be 2t sine 40 minus force of gravity. I then can add the force of gravity to the other side, so plus ft, ft. So that's going to give me Fg is equal to 2t sine 40. Force of gravity is mg, so I'll go ahead and make that substitution. So that's mg is equal to 2t sine 40. I'm doing lots of the math steps here for you. In this, we're going to divide. We're trying to solve for t, so I'm going to divide both sides by 2 sine 40. So on this side, I'm going to get mg divided by 2 sine 40 is equal to t. So then just plug in, mass is 0.5, g is 9.8, 2 sine 40. We can type that all into our calculator. We're going to get that t is equal to 0.5 times 9.8 is going to give you 4.9. 4.9 divided by 2 sine 40 is 3.8. There you go. You're done. Real quick, you might find it useful to do 2 times by the sine of 40 when calculating this. You might find it useful to be like, okay, this is actually 4.9 divided by because 0.5 times by 9.8 is 4.9 divided by 2 sine of 40 is 1.29. So that then 4.9 divided by 1.29 is where the 3.8 comes from. So you might find it useful to break that down even further. Okay, well, that is both our example problems. I hope you find this useful. Let me know if you need any extra help, and thank you for watching.